The false dawn, the arsenic life controversy. While that was happening in field stations and salt flats, a different story lit up the world and burned out just as fast. December 201. NASA teased an astrobiology announcement that would impact the search for life. Cameras, headlines, the whole stage. The claim: a bacterium from Mono Lake, GFOG1, could swap arsenic for phosphorus in its biochemistry, maybe even in DNA. If true, it cracked open the periodic table and cracked our assumptions about life's fixed parts. It sounded like a backdoor to the Shadow Biosphere. Here's why it hit so hard. Phosphorus is a backbone player. DNA, RNA, ATP, membranes. Pull it out, and most intro textbooks collapse. The idea that a microbe could jam arsenate into those jobs broke rules that felt carved in bedrock. And Mono Lake wasn't random. It's hypersaline, alkaline, arsenic-rich, exactly the kind of niche where weird chemistry might thrive. The story wrote itself. Newspapers ran with alien life, and the internet did the rest. In lab rooms without microphones, skepticism started immediately. Chemists pointed out that arsenate esters are notoriously unstable in water. They hydrolyze fast. If DNA had arsenate in its backbone, it should fall apart between coffee breaks. Microbiologists asked dull questions that matter. How pure were the reagents? How low was the phosphate carryover? What did isotope tracers say about real incorporation versus surface contamination? And could the microbe simply be scavenging trace phosphorus with desperate efficiency, the way many cells do under stress? Within a year, independent teams ran the controls that should have come first. They grew GFAG1 in carefully phosphate-limited media, tightened contamination, and layered in radioisotopes and mass spectrometry. The result? The bacterium tolerated high arsenic, but still depended on phosphorus. No arsenic backbones in DNA. No biopolymer swap. The early signals were artifacts: carryover phosphorus, impurities, misinterpreted mass peaks. The study that launched the frenzy got picked apart in comments, replies, and years later, formal retraction. Careers were dented, trust took a hit, and arsenic life became a cautionary hashtag. This wasn't just a pile-on, it was a lesson plan the field needed. Extraordinary biology doesn't get to skate by on unusual growth curves or provocative phrasing. You need isotope tracers that follow atoms into bonds. You need rigorous chiral and chemical separations to rule out lookalikes. You need pre-registered protocols, so post hoc rationalization can't move goalposts. And you need independent replication. Other hands, other benches, same outcome before the press conference. Unknown to them, across town a different group was laying out agnostic life detection frameworks that would have averted some pain. Design assays that don't assume a single backbone. Use multiple orthogonal measurements. Mass spectrometry to profile families of compounds. NMR to see connectivity. Chiral chromatography to separate enantiomers instead of averaging them. Build negative controls that mimic every contamination path you can imagine. Then try to break your own claim. Here's the part that matters for mirror life. The arsenic saga didn't kill curiosity, it forced discipline. If someone brings you a mirror microbe tomorrow, the bar is high and specific. Show growth in racemic media where only one enantiomer disappears, tracked by stable isotopes, so the math isn't hand-wavy. Demonstrate that our proteases don't digest its proteins in real time with controls that prove the proteins are debuilt. Flip our go-to antibiotics to their opposite enantiomers and see if activity swaps as predicted. Use peptide nucleic acids or other achiral binders to fish out heredity without assuming D sugars. Publish the plan before the run. Invite rivals to replicate. There's a human layer too. The NASA rollout magnified a normal scientific tug-of-war into a culture war. Hype promised an answer the data didn't earn, and the correction looked like embarrassment rather than progress. The fix isn't silence, it's pacing. Let the boring graphs pile up. Let the controls get so tight they squeak. Then tell the story with the caveats intact. The audience can handle nuance. What breaks them is the whiplash. In the aftermath, we got better tools and thicker skin. The arsenic lake still shimmers. Extremophiles still surprise us. And the Shadow Biosphere hypothesis survived because it wasn't tied to that claim. If anything, the false dawn clarified what sunrise has to look like. No fireworks, just a stubborn signal that survives every way we try to erase it. Now with guardrails in place, we can build the net that doesn't assume our chemistry and see what it catches. Building the net, how you'd actually find mirror life. With the guardrails bolted on, you stop assuming and start fishing. The trick is to build a net that doesn't prefer a hand. Culture independent first. Mass spectrometry has carried spacecraft and clean rooms for decades. Now it has to carry our blind spot. Instead of scanning for a short list of familiar metabolites, you profile entire families, masses, fragments, and isotopologues without locking to L-amino acid databases. Time of flight or orbit trap systems, coupled to soft ionization, map the chemical zoo. Tandem MS peels the onions. If biology is selecting one hand, you'll see odd depletion patterns in a racemic feed or recurring series that match peptides only if you flip every residue. That's an agnostic hit. Meanwhile, NMR gives you geometry without prejudice. It doesn't care about your alphabet, it cares about how atoms sit and wiggle. Two-dimensional spectra reveal connectivities, coupling constants, and the subtle shifts that betray stereochemistry. Pair that with circular dichroism and vibrational circular dichroism, bulk signals of homochirality, and you're sniffing for the one property we expect life to flaunt, no matter which toolkit it chose: consistent handedness across polymers. A racemic soup cancels itself. A living system leaves a tilt. But graphs don't eat, so you bait. Enzyme assays can be turned into interrogation rooms if you set them up in pairs. Put out L-sugar-specific enzymes beside these sugar-resistant versions and watch activity when you add environmental extracts. If the wrong assay lights up and the right one dies, you've got a clue. More rigorous, build mirrored enzyme pairs where the only difference is the chiral center of the substrate. Track activity over time with stable isotopes, 13C or 2H, embedded in just one enantiomer. Then follow the heavy carbon into downstream products by mass spec. If the heavy label migrates only when the mirror enzyme is present and not when the native one is, you're seeing preference, not inhibition. Now set the table fairly. Racemic media, 50-50 buffets of amino acids and sugars, remove the starvation excuse. See parallel microcosms with your sample. In one, the D enantiomers carry a heavy isotope. In the other, the L ones do. If respiration rises while only one label pool disappears, you've separated appetite from artifact. Do it under anoxic and oxic conditions, warm and cold, so you don't confuse thermodynamics with taste. Every time you flip which hand is heavy, the consumption pattern should flip too, where you're looking at chemistry, not life. Physical separation makes the accounting honest. Chiral chromatography columns split twins that look identical to most machines. After incubation, you pass the leftovers through those columns and quantify which hand remains. If biology favored one, the chromatogram shows a clean asymmetry, where a racemic control stays even. Stack the methods: LC-MEMS for quant, NMR for structure, chiral LC for separation, isotope ratio, MS for tracing. Each orthogonal angle closes a loophole GI-HG1 slipped through. Heredity can't hide forever if you don't force it into our mold. PCR is a non-starter if the backbone is different, but peptide nucleic acids, achiral scaffolds that bind by base complementarity, can fish out templates regardless of sugar hand. You design short PNA probes against plausible motifs, purine-pyrimidine repeats, hairpins that stabilize replication, and see what sticks. Alternatively, skip letters entirely and chase translation surrogates. Shotgun proteomics, done with search spaces that include both L and D residue possibilities, can detect periodic masses and fragmentation ladders consistent with peptides built from the other side. If spectra fit only when you invert every chiral center, you've got more than noise. Here's a micro story from a pilot run that tightened our plan. A team at a salt flat set up twin bioreactors with racemic lactate labeled on one hand per tank. The gas sensors showed CO2 rising in both, but only one reactor lost a labeled hand. The other chewed the mirror. They swapped labels, repeated the run, and the preference swapped with it. Then they tried protease spikes. Our proteases erased activity in the tank, preferring L-lactate, but barely dented the other. The signal wasn't fireworks, but it didn't flinch when they poked it. That experiment didn't prove mirror life, but it proved the protocol could corner it if it was there. Antibiotics add a clean stress test. Many target stereospecific machineries, ribosomes, cell wall enzymes. You dose parallel cultures with an antibiotic and its enantiomer. If one is inert and the flipped version bites, you've mapped the handedness of a living target without sequencing a base. The same logic works with phages and viruses built for us. If nothing happens in either direction, keep that in the maybe pile, but don't overread silence. Meanwhile, build failure into the design. Spike controls with known inhibitors to show how a flatline looks when chemistry, not chirality, is the culprit. Run abiotic reactors with the same media and minerals to learn how non-living chiral biases drift over time. Every path that could fake a signal gets a test lane. Then pre-register the entire playbook, share raw data, and invite people who don't like you to try to break it. This is how you net a shadow without catching your own reflection. No single assay screams mirror life, but a stack of consistent preferences, eating one hand, resisting our proteases, flipping drug responses, leaving chiral fingerprints across pathways, builds a case the headlines hideouts. Only where then mirror life would survive us. Everything was about to change when we asked a blunt question. If a mirror lineage can't eat our world, where could it quietly build its own? You don't hide in the buffet you can't taste. You hide where competition is thin, gradients are steady, and chemistry nudges choices. Start with brines that bite. Hypersaline pools turn our enzymes sluggish. Water activity drops, proteins misbehave. Yet haloarchaea dance there, proving life can hack extremes. For a mirror lineage, saturated salts are more than a test. They're a moat. If your metabolism evolved to prefer D proteins and those sugars, you'd want a place where our grazers and phages barely function. Enclosed basins, salinity stacks by season. The chemistry's predictable. A mirror web could idle there, metabolizing slowly, leaving thin films that standard stains ignore because the dyes bind our stereochemistry better than theirs. Slide down the pH scale to pools that eat boots. Hyperacid springs and fumaroles shave away vulnerable bonds. Our decomposers lose their edge. Acid strips membranes, ruins proton gradients, unless your toolkit is tuned to those slopes. Mineral surfaces at vents can bias absorption chirally. If calcite faces or clays sort enantiomers even a little, local microenvironments might feed a mirror preference just enough to bootstrap. Picture a biofilm thinner than paint, clinging to a flowstone where dissolved iron flips redox back and forth like a metronome. Lab assays would read trace organics, odd enantiomeric excess, likely abiotic. Then you swap to racemic probes and the pattern sharpens. Meanwhile, under our feet, kilometers of rock hold time like a freezer. The deep subsurface runs on crumbs, hydrogen from water rock reactions, sulfate trickles, slow methane. Metabolism there is patient. Generations stretch. Isolation lasts geological chapters. That's perfect for a lineage that doesn't mix with ours. You're not competing with fast surface cycles, and racemization clocks tick too slowly to erase homochirality in living systems. Pore networks and fracture waters could shelter mirror cells from predatory webs. Every sample comes up warm with abiotic signals and sparse biomass. Our primers find nothing, our cultures starve, and we shrug. But give that water a 50-50 buffet in a month, and you might see one hand fade. Hydrothermal chimneys are the other big bet. Alkaline vents lace microscopic compartments through mineral walls. Natural proton gradients hum. Metal sulfides catalyze reactions relevant to both origin stories and sustained life. Crucially, mineral chirality and flow geometry concede tiny biases. If two protometabolisms started in adjacent microcaverns, one could drift left, one right, never mixing beyond small molecules. Think of powerhouse stacks, billions of reaction cells, where selection pressures diverge on millimeter scales. From our perspective, vent scrapings look like complex organics smeared across iron and nickel. From theirs, it's home. Then there's ice, the subglacial brines threaded through Antarctica's buried lakes and Greenland's base. Salt depresses freezing points, water films persist, and nutrients arrive as whispers. Low temperature slows everything, including enzyme decay and diffusion. If mirror proteins resist our proteases, they'd be doubly stable in cold. A mirror cell could cycle once a year and still hold territory. Our probes, tuned to our membranes and markers, bounce. But circular spectropolarimetry over a meltout might catch bulk homochirality where none should sit without biology. Desert varnish writes messages we can't always read. Those glossy manganese-rich skins on rocks accrete over centuries. Microbes contribute, dust helps, chemistry does the rest. Some varnish layers show chiral excess in tightly bound organics that doesn't match local plant inputs. We chalk it up to sorting on mineral faces or photolysis quirks. What if a fraction of that sheen is a mirror film living so slowly we mistake it for weathering? Scrape, dissolve, run chiral chromatography. Then run it again after an incubation on racemic feeds. If one hand thins in the scrape that sat with mirror-friendly nutrients, you're onto something. Planetary analogs help pick targets. Mars hosts chloride deposits and recurring brine activity. Europa's ocean cycles salts under radiation that can drive unusual chemistry. We're not leaping to aliens. We're rehearsing Earth's side. The logic is this: environments that select for homochirality by physical means, sorting on minerals, biased photochemistry, constrained diffusion, give mirror-life scaffolds to stand on. Identify those scaffolds here, test protocols, then carry that playbook to places where our biosphere never booted. Here's a micro story that stuck with a field team. A researcher in Chile's high-altitude salars swabbed a purple slick above an evaporate layer. In camp, their standard enzyme panels did nothing, a racemic lactate. Microcosm, thrown together as a why not, crept upward in CO2 after a week at night temperatures. They chased it with chiral LC. The D-lactate pool thinned, the L pool barely budged. They repeated, flipped labels, got the mirror result. Then they added our proteases. Activity in one set collapsed. The purple slick set barely flinched. They didn't call a press conference. They called for more salt, more time, more controls. One more hideout sits in plain sight. Human systems. Water treatment plants, industrial fermenters, hospital plumbing. Biofilms accumulate where chemistry fluctuates and cleaning selects for outliers. If our disinfectants and enzymes bias against our own handedness, the mirror tail of a mixed population, if it exists, could become the head in those corners. A drain that resists every usual biocide but falters, when you swap to enantiomeric detergents, would be less a nuisance and more a signal. It's a place to watch, not fear, unless we ignore it. So we choose hideouts where selection lowers the noise, where our biology moves slowly, where chirality can lean without toppling. If a mirror lineage survives us, this is where it waits. And if we're careful, this is where we'll meet it first. The firewall. Why mirror life doesn't mix with ours. While those hideouts simmered away from our attention, something else explained why we hadn't already collided head-on. Geometry builds a firewall. Not a wall you can touch, one made of shapes that refuse to handshake. Our enzymes were carved by evolution to clasp L-amino acids and D-sugars. Flip the hand and most interactions slip. Metabolism turns into a room full of doorknobs that don't fit any key you have. Start with breakfast-level biology. Transporters in your gut pull specific sugars across the lining, but they're asymmetric pockets. Glucose tastes sweet to your tongue, but ghost walks past those pumps and exits the other side because nothing grabs it. Scale that to a cell trying to eat a mirror bacterium. The praised proteins and polysaccharides present surfaces with the wrong twist. Our digestive enzymes bite air. Even scavenger enzymes that chew debris stall because their catalytic centers are stereospecific. That's nutritional isolation, the cleanest reason parallel food webs could sit centimeters apart and never meet. Drugs don't cross the gap either. Most frontline antibiotics hit ribosomal RNA folds, topoisomerases, cell wall assembly lines, targets with chiral architecture. Switch to a ribosome built from mirror components, and those binding sites invert. The drug's shape no longer complements the pocket. Activity collapses. It's not universal. Some antibiotics disrupt membranes or redox broadly, but the heavy hitters are shape readers. In a mirror lineage, you'd expect our staples to miss, and in some cases, their enantiomers to gain potency. That's a quick, diagnostic, and a sobering clinical blind spot.